Okay, up to now we've used matrices as a shorthand for systems of equations. We've done a lot with this. Solving systems of equations is going to be a valuable tool for us. It turns out, though, that we can use matrices for other things. There are several other really important things that we can use matrices for. At the moment, I can't tell you what these other things are. Those will come later. But rest assured that there are these other things that we can use matrices for. So what I want to do is I want to develop some algebra of matrices. The algebra that we're about to develop is going to be extremely useful for these other applications of matrices. And that algebra, for the moment, we're just going to think of matrices as being completely independent things, independent of an application. They're just algebraic structures that we're going to define algebraic operations with. Okay. All right, so we'll start with matrix addition. Now, the good news is that the formula for matrix addition is very easy to write down, and it's very easy to work with. The bad news is that the motivation for this formula that I'm about to show you is based on how we can think of matrices as being used for these other things that I have yet to tell you about. So I'm not going to be able to currently give you a motivation for this formula for matrix addition. I'm just going to show you the formula. So here it is. If you want to add two matrices, specifically matrices for which you know the individual elements, so this is the notation we're going to use, by the way. This notation says that in the ij entry of a matrix, this a sub I comma j is the entry in that position in the matrix. Okay. Again, that means ith row, jth column in the matrix. Okay, so if you know the entries in the matrix A, and if you know the entries in the matrix B, then the way you add them, the sum matrix C has the feature that its entries, you want to know what its entries are, they're computed by that formula. Altogether, what this says is you just add entries one component at a time. The ij entry in the sum is the ij entry from the first matrix plus the ij entry from the second matrix. So even more explicitly, if you want to know what this is, well, it's the sum of the corresponding entries in the two matrices that you're adding. If you want to know what that is, it's the sum of the corresponding entries in the matrices that you're adding, etc. Okay, so very convenient. What you're going to want to call natural formula. But I emphasize that we can't really choose to view this as natural yet because algebraic convenience is not what natural is about. We're going to interpret this as natural after we see how this relates to interpreting matrices as representing these other things. That will make this formula seem natural. Okay. Similar story for scalar matrix multiplication. There's an easy formula for how to multiply a matrix times a scalar. And the formula is that you just, in order to get any entry of the product matrix, you take the corresponding entry of the original matrix and multiply by that scalar. Said differently, that scalar multiplies by all of the entries of the given matrix to get the corresponding entries of the product. Very simple little formula. So you see here this 5 is multiplying by all of these entries to give me that. Okay. So again, very convenient formula, easy to compute with. Not immediately obvious why this is natural, but it will be seen to be natural once we see these other interpretations of matrices. Okay, now here's where it gets a little bit tricky and seemingly unnatural. That's actually still natural. It's going to look weird. So this is matrix multiplication. So an odd little formula. I suspect many students in this class have already seen this formula for how to multiply two matrices. So I hope this will look familiar. If it doesn't, no problem. I do want to warn you, though, that the presentations that students have usually seen prior to this class on the nature of matrix multiplication is usually pretty light and not sufficient for our purposes here in Math 216. And I'll say more about that as we go along. Okay, so matrix multiplication. First, a little bit of bad news. there are certain requirements. You can't just multiply any two matrices. So we need for the number of columns in the left matrix to equal to the number of rows of the right matrix. That's just a requirement. If this isn't satisfied, you can't multiply these matrices. Again, I claim this is very natural. We'll see that later on in the course. All right. Now, another way to phrase this same thing is that the number of elements in a row of the matrix has to equal to the number of elements in a column of the matrix. Now, these look like different statements, but these are actually the same statement because these are really the same thing. The number of columns in a matrix is, in fact, the same as the number of entries in a row of the matrix. I just look at this example and see that in fact, for every row, each entry in that row corresponds to a column. So the number of columns is the number of entries in a row. Okay, nice fact. And then likewise for the number of rows of B versus the number of entries in a column of B. And again, there's a one-to-one correspondence between these. For every column, each entry corresponds to a row. Okay, so we do need these numbers to be same. Now, again, you can view this in either context. You can view it as the number of columns of A got to equal to the number of rows of B. You can view it as these numbers have to be equal. Or you can view it as the number of elements in a row equals the number of elements in a column. They're equivalent. They're equivalent statements, but they just look a little bit different. Okay, so this requirement has to be satisfied. And with that requirement satisfied, here's how you compute. If you want to compute an entry in the product matrix, this product matrix C, product of A times B, the way you compute that entry is with this formula. It's a dot product. So think back to Math 212, by the way. A dot product means you take the entries in this row. This is the notation we're using for the ith row. Let me remind you up here. This notation here indicates one of the rows of the matrix. And then we're going to do a dot product with the corresponding column of the right matrix. And notice this notation, the lowercase with a subscript indicates that we're talking about one of the columns of the right matrix. Okay, so for example, if I want to compute this entry of this product matrix, now first of all, let's check, can I actually multiply these matrices? Am I allowed? Well, the number of entries in a row of the left matrix does, sure enough, equal to the number of entries in a column of the right matrix. Said differently, the number of columns of the left matrix equals the number of rows of the right matrix. Same statement, different point of view. And I compute that entry by taking a dot product of that row, that's the corresponding row that the entry is that I'm interested in, with that column, and notice first column corresponding to the fact that the entry I'm interested in is in the first column. Okay, and that dot product, a little bit of arithmetic, you can persuade yourself, is 21. Okay. Similarly, if you want to compute that entry, it's in the first row, so we look at the first row. It's in the second column, so we look at the second column, and again, do the arithmetic on the dot product, and you get that value. Okay, so I think this formula is a formula that students have primarily seen in high school presentations. It is computationally convenient, computationally efficient. In fact, if you're reasonably decent with arithmetic, that means that you can pretty much write down all of the entries in this product matrix, at least if the matrices are reasonably sized, without even writing down any work. So that's highly appealing from an arithmetic, computational point of view. Okay. Important point to realize, though, that is not our primary interest. And our primary interest in this class is not to learn how to compute stuff. Our primary interest in this class is to understand how objects of interest relate to other objects of interest. Now, certainly there is some of that in here, seeing how entries of the product relate to rows and columns of the other matrices. This is useful information, and we will make useful gains from this that point of view. But there are other really more valuable points of view on how this matrix multiplication works. Equivalent points of view that have greater upshots. So let me show you the first one of these. So instead of looking at the product matrix and thinking of how to compute it one entry at a time, we're going to think of how to compute it one column at a time. So here's the idea. A column of the product matrix turns out to be a linear combination of the columns of the left matrix. That's an interesting fact, right? This is a relationship between objects of interest in this calculation that maybe you hadn't seen before. This column is a linear combination of those columns. Okay. What linear combination? Well, it's a very specific, particular linear combination. It's a linear combination where I use the corresponding column of B. Now, by corresponding, notice this is the first column, so the corresponding column of B is that first column. Those are the numbers that I use as coefficients. So, as I have written over here, the explicit linear combination that we use, the linear combination is that this column of the right matrix is a linear combination of these columns of the left matrix, and you see that I'm using the corresponding column of the right matrix to give me my coefficients. Right? And you can again do this arithmetic, the arithmetic in this linear combination. Hard to work that out and persuade yourself that sure enough you get that 19 and 43. And if you want to check and make sure that this has worked correctly, of course you can just compute this one entry at a time. So that dot that and confirm that it gives you 19. And likewise this is that dot that. And again, that's just arithmetic. Now, I'd like to persuade you that it's not a coincidence that these two seemingly very different formulas give us the same thing. In fact, the dot product point of view can be viewed as a consequence of this linear combination point of view. So now we agreed that this is a linear combination of those, and so let's ask now, what does that have to do with this first entry in that column? How would I find not the whole column, but how would I find just that first entry? Well, if the column is a linear combination of these columns, the first entry would be the same linear combination of these first entries. Right? So that's a linear combination of these. That is the same linear combination of those. Well, linear combination, of course, with these coefficients. So that 19, this is a linear combination of those using those coefficients, and that's a dot product. Right? A linear combination of numbers using certain coefficients is just a dot product. You can see it right there. So not too hard to see why it is that this works. This linear combination point of view just sort of combines all of the various dot products, or many of the various dot products together into this larger linear combination computation instead of individual dot product computations. Okay. Again, this is an interesting point of view because it relates objects of interest, namely columns of the matrix. Columns of the left matrix over here and corresponding columns of the right matrix. Okay, nice fact. Here's another alternative point of view. There's a similar fact about rows. Again, a bit unexpected. Okay, so instead of computing one entry at a time, here we will compute the product one row at a time. Well, the rows of the product are linear combinations of the rows of the right matrix. Which linear combination? Well, a linear combination using the corresponding row of the left matrix. Corresponding because, well, I'm computing the second row of the product. The coefficients then are the second row of the left matrix. So let's see, what does that linear combination look like? Well, this is the linear combination particular that we're looking at. These rows that we're taking linear combinations of, here they are. Notice I'm writing them as rows. The coefficients that we're using, those numbers 3 and 4, and multiply that out and do the arithmetic, and note that sure enough we do get that correct product. Okay, so interestingly, not only can I think of matrix multiplication as a statement about linear combinations of rows, I can also think about it as a statement about linear combinations of columns. Now you do have to be careful. The rows and columns play different roles. When you're taking the column point of view, you're taking linear combinations of the columns of the left matrix. When you're taking a row point of view, it's linear combination of the rows of the right matrix. Likewise, when you're taking a column point of view, it's the columns, it's the columns of the right matrix that give you the coefficients. When you're taking a row point of view, it's the rows of the left matrix that give you the coefficient. So this is it looks a little bit backwards. You have to make ultra sure to make sure you remember which way it goes. If you get it backwards, you will get a wrong answer. It is not flexible on which way this goes. Okay, last point of view I want to show you on matrix multiplication is it's really just notation, but the sigma notation can be very useful. It has the nice feature that it's extremely explicit. So this is a sigma notation perspective on how to multiply matrices. Now you'll notice that the matrices that we're starting with, again, I have a matrix A with certain known elements, C, certain known elements. C is the product of those two matrices, and I want to talk about the elements in that matrix C. And notice we have here an explicit formula for how to compute those elements. So we call this sigma notation because we're making use of the sigma summation idea. This is the same summation that's used for Riemann sums, and I know students have seen this in single variable calculus classes. It's used, of course, for series calculation, so students should be very comfortable with this notation. And now let me just walk you through why this, as a summand, well, let's say it differently, why this, in fact, does matrix multiplication for you. Okay, so let's write out some matrices here. Oh gosh, I ran out of space. Let's try that again. Okay, so if you're multiplying some matrices, notice we are interested in computing the ij entry. So being as we are in the ith row, say we're in the ith row here, that means we're going to be looking in the ith row of the left matrix. Okay, and now we're also, you'll notice, looking in the jth column. I'm interested in the entry in the jth column here. So being in the jth column, I will look correspondingly at the jth column of the right matrix. Okay, so what I'm going to be doing is I'm going to be taking entries from that ith row and multiplying them by entries from this jth column and multiplying and adding. And of course you see here we are multiplying and adding. Okay. All right, so let's just talk about these subscripts here and how do those subscripts do what we what we wanted to do. Well, let me clear out those dots. These entries here in this ith row, one thing you'll notice is that because we are exclusively in the ith row, note that the first subscript is always I, because we are staying in the ith row. And it's just that as we move along, as we move across, right, the column number, which column we're in, is going to be changing as I go through the terms in this summation. So the column number is what goes from 1 to n. Right, K going from 1 to n, K being the column number in these subscripts, is what has me then going across that ith row. And likewise, analogously, this is what has me going down the jth column. So you'll notice that the B references, it's always the jth column. Right? The subscript is always, the second subscript of B is always J, indicating that I'm in that jth column. So how do I move down that jth column? Well, I move down that jth column by making reference to different row numbers. So these different row numbers going from 1 to n takes me down that jth column. So all we have here then is, in fact, that I'm going along the ith row of the left matrix, along the jth column of the right matrix, and I'm multiplying and adding. That's all that expression is. So this sigma notation, again, has a nice benefit that's extremely explicit. Right? Nothing left to the imagination about exactly, precisely which numbers are we talking about. The disadvantage of this is a little bit hard to read, so you might sometimes be able to find ways to avoid using sigma notation, and that might be considered desirable. But certainly sometimes you can't avoid it. Certainly sometimes you will be faced with it. In other words, the notation that you'll be looking at will whatever it is that you're looking at will be given to you in sigma notation. So it's important to understand what this notation means and how to make sense out of it.